Now, regarding polar and nonpolar covalent bonds, this is a special periodic table. It's actually just part of a periodic table. And instead of the atomic masses at the bottom, they have these numbers here that look like grade point averages. This is on a 4.0 scale. 4.0 is the highest number here, and then 0.8 or something like that is the lowest number here. This is just like grades, where 4 is an A, and 3 is a B, and 2 is a C. These numbers on this 4.0 scale show how strongly these atoms suck up the electrons in a chemical bond. So, for example, in a chemical bond, if you have carbon bonded to oxygen, oxygen has a 3.5 score on that scale. Carbon has a 2.5 score on that scale. Here's carbon, 2.5. Here's oxygen, 3.5. That means the difference here, the difference is 1. Now, that difference, 1, that means that oxygen wins here. Most of the electrons in this bond go towards the oxygen. So that means that this bond is going to look like this in real life. The electrons are going to be mostly with the oxygen. You see, this strange shape that I've drawn shows you where the electrons are spending most of their time. Most of the time, the electrons are over here. Actually, there are only 2 electrons in this chemical bond. So those 2 electrons are usually on the oxygen side. Sometimes they are on the carbon side, but usually they are on the oxygen side. Why? Because oxygen has a stronger pull for the electrons than carbon. The difference on a 4-point scale of the strength of oxygen's pull compared to carbon's pull for these 2 electrons is 1. Any difference that is greater than 0.5 is going to give you an uneven pull. What that means is that's going to give you a polar bond. Okay, so that is a difference between the polar bond and the nonpolar bond. It is this difference. Let me give you another example. Carbon and hydrogen. Carbon has a strength of about 2.5. Hydrogen has a strength of about 2.1 in pulling electrons in this bond, these 2 electrons in this bond. You see the difference is 0.4. Now 0.4 is not greater than 0.5. So this bond ends up being a nonpolar bond. Okay? Does that make sense? Please ask me questions by email, or you can remember to ask me a question in class. It's best if you ask me by email now, so you don't forget to ask me in class if this is not clear. I'm about to show you a picture to help you to understand this. All right? Here's the picture. Here I have an atom. Here I have another atom. All right? Now, I'm going to control the strength of this left atom. If I make that left atom weak, notice that the 2 electrons in the bond between the atoms like to spend their time around the right atom, because the right atom is much stronger than the left atom here in terms of pulling electrons within this bond. There is a color code here that shows you some difference in charge. The charge difference here is pink for slightly positive and light blue for slightly negative. Notice that it is not red here like that. It is not just dark blue here like that. And the reason is the electrons in this bond are shared. This is not a positively charged atom. This is not a negatively charged atom. There may be a partial positive charge here and a partial negative charge here, just because the electrons in this bond are being shared unequally. But there is no full positive charge or full negative charge here. Okay? Now I'm going to control the right atom's strength in pulling electrons of the bond. Okay, now here I have made the left atom very low and the right atom very high. So in this case, this is not a covalent bond anymore. This is now an ionic bond. You see there's dark red here and dark blue here. That means this atom is now fully charged. It's a negatively charged atom. It has taken away the electron from this atom. This atom has lost an electron, so it is fully charged. It has a +1 charge here. So this is now an ionic bond. Now, I can play with this to make any combination of strengths. Now remember, these strengths go on a 4-point scale. I can make it ionic the other way. I can make it, you could see that the polar covalent, nonpolar covalent, the difference between polar covalent and nonpolar covalent is sort of on a continuum, meaning it could be a little less polar covalent or it could be a little more polar covalent. Do you know what I mean? Just like it could be, let's see, more nonpolar covalent, or it could be a little less nonpolar covalent. So that's that makes it hard to define. Is this bond going to be polar covalent or nonpolar? Polar or nonpolar? So to help you to define that, I'm using the number 0.5. If the difference here is less than 0.5, which this difference is, then we're going to call that nonpolar. And then if the difference is more, if the difference is more than 0.5, like this, we're just going to call that polar. Okay? So I hope this picture helps you there. I can bring this picture up again on the projector in the lab session on Monday. If you need it, just ask me in class or send me an email. Now, that is going to give you the answer to this question. Is there a polar bond in this molecule? You just have to say yes or no. And then you should circle the polar bond. Okay? Here's what I mean. Right. Here I have the Lewis structure that I drew in the previous video. And there's a C and there's an H here. I'll do this in a different color. The C, remember that the C was 2.5 on the scale of the strength of pulling electrons. Here it is. C was 2.5. And remember the H was 2.1. So the difference between C and H is only 0.4, so that's nonpolar. There's another CH bond here. That's also nonpolar. Now, the chlorine was 3.5. So the difference here is 1. And the difference here is 1. So this is a polar bond. I'm circling it. And this is also a polar bond. I'm circling it. Okay? So I'd like you to do that too. When you draw your structure, I want you to circle the polar bonds. And I want you to say yes, that there are polar bonds, or no, there are no polar bonds if you didn't circle any. So it should look like that. Circles or no circles. You don't need to write these numbers there. I just want you to circle the polar bonds. You can write the numbers here if you want. Now, what about dipole arrows? Dipole arrows are something that you should draw on this. So, dipole arrows are the arrows that I drew for you in this other picture. See this right here? This is a dipole arrow. It has a cross on it. The cross goes to the slightly positive side of the chemical bond. Let me do this in a different color. So this dipole arrow points to the atom that has the higher score. It points away from the atom that has the lower score. Right? So you draw it like this. I want you to draw that for all of the polar bonds in your 3D sketch. I don't want you to draw this for any of the nonpolar bonds. show you exactly what I mean. Go back to the 3D sketch. Here's my 3D sketch. You see that the CCl bond is polar. So I'm going to draw it this way. Why is it not this way? It's not that way because carbon is 2.5 and chlorine is 3.5. 3.5 is more than 2.5. The arrow needs to point to the stronger atom, okay? And then I want you to draw it over here also, carbon to chlorine. Are you going to draw it for carbon to hydrogen? No, because remember, carbon is 2.5, hydrogen is 2.1, the difference is only 0.4. We're going to assume that that difference is not great enough to make this bond polar. We're going to use number 0.5. Remember that? We're going to use number 0.5 to decide whether the difference is great enough for the bond to be polar or not. Right, back to the picture of the 3D sketch. So your 3D sketch needs to have arrows just like this with the cross portion of the arrow near the weaker atom for pulling electrons in this bond, and the arrow pointing at the stronger atom for pulling electrons in this bond. Thank you.